Hello, so this is the second installment of my series about making that noise toaster analog synth. So the material I'm presenting is, I mean, at least the schematics are coming straight from the book Make Analog Synthesizers by Ray Wilson, the guy from music from outer space. And again, this is about the noise toaster synth. So last time we talked about that envelope generator, and today we're going to talk about the LFO, the low frequency oscillator. So this is the schematics taken straight from the book. And the output is actually either a square wave, some kind of fake triangular wave, and some kind of weird thing that I'm not sure what it is. I'll talk about that one and that one briefly later. And there's also in the schematics an LED that is going at the same rate as the LFO, so that you get a visual cue about your speed. But I'm not going to talk about this because it's kind of useless, to be honest. So I'm going to focus primarily on this area right there. So in order to get the square wave is using an op amp. LM324 is a quad op amp. It's using only 1/4 of it, and it's just your regular op amp with a non-inverting input and an inverting input, and this is your output. And he's using that op amp as a comparator, and that's how you can get a square wave when you use not only negative feedback, so that's a negative feedback loop here, but also positive feedback. Recall that you always use positive feedback when you use an op amp as a comparator. And notice also in the negative feedback loop you have the capacitor here, and that's basically the key to create oscillations here. What I'm gonna do is that I'm gonna simulate that thing in LTspice, and we're gonna look at the results. So let's go into LTspice, shall we? Okay, so this is LTspice, and this is how I simulated that thing. So again, I kind of streamlined the design a little bit so that I can only focus on the square wave generator. So this is the heart of the thing. This is the op amp that's used as a comparator. So you have a VPOS and a VNEG, which is +10, -10. I use +10, -10. I have no idea why. I don't know what he's using actually in the book. All I know is that the BP is the battery positive and the BN is the ground. And for BP, I know he's using 9 volts. So what do we have here? So we have the op amp here, again used as a comparator. This is V out, so you have this loop, negative feedback loop here, negative feedback loop, and there's a capacitor here. That's the important thing. And here is just a pot to control the rate of your LFO. Okay, so, and as you know, when you do the comparator, to have some kind of hysteresis, see like the Schmidt trigger circuits, you need to have a positive feedback loop. So you also have a positive feedback loop. That's that one. That's your positive feedback loop. And here you have a voltage divider to kind of control this voltage here. So this is basically the plus here is the threshold. This is the threshold voltage. And as you know, if V minus, this is the voltage at the inverting input, is below V plus, then the output is at the saturation, the high saturation, so +10 volt. If the voltage at the minus input is above V plus, then the op amp is going to go into saturation, but the other way around, so the low saturation, -10 volts. Okay, so let's try Maybe I should just run it so that you have an idea of what's going on. So if I run this thing, and here I use some kind of value here for the pot. So if I run this thing, okay, so let's look at the output. Let's look at the V+, so the voltage at the non-inverting input. And let's look at the voltage at the inverting input. So let's have a look at that stuff. So you have 10 volt, so that's the positive rail, and that's the minus 10, negative rail. So the green is the output. The green is the output. That's your square wave output. The blue is your threshold. So that's the voltage at the non-inverting input. Okay, and as you can see, it kind of follows the output. And it goes up here to 6.33 volts. And the red one is the voltage at the inverting input. And just by looking at this, you can have kind of a clue of how it works. So here, the V minus is under the V plus. Again, V plus is the threshold. So it means that the output is going to be high saturation. And this is the capacitor charging, by the way. So as soon as this red thing goes above or tries to go above here, okay, so you have a switch. It goes into minus 10 volts. So it goes into low saturation. And when this happens, the blue one also at the same time goes to 0. And then this guy discharges. And as you can see, the red is above the blue, and the blue is the threshold. So that means that you are in the low saturation. So that makes sense. So let's go back to the circuit and try to understand how it works. So let's assume that at the beginning of times, the capacitor is discharged, and let's assume that the V out is high. So it's going to be plus 10 volts. So you have plus 10 volt here. So for sure the current is going to go this way, and it's going to charge that capacitor, C16 right there. So it's going to charge it from 0 to towards V out. So it's going to charge. So it's basically, when you look at it's going to go like this. Yeah, this is the charging of the capacitor, the red one. Okay, this part. So it's going up. So then what happens on the positive feedback loop? So you have plus 10 volt, and here you have 4.5 volts. But this is not going to stay at 4.5 volt because of this 10 volt to 4.5 volt differential. Basically, there's current going in here. There's going to be current going this way. So the voltage divider formula doesn't hold anymore because you now have current in this branch. So this guy is going to go up. So this guy is going to go up, and it's going to reach 6.3 volts. So that's what you see here. You see is here, 6.3 volts. This is 6.3 volts. Okay, so we are somewhere here, let's say. Okay, so this one is 6.3 volts, it doesn't change, and this one goes up because it's charging. When the voltage here reaches 6.3 something volts, what's going to happen is that when we reach about here, and then the capacitor goes slightly above, let's say, right away, the op-amp output is going to switch and go to a low saturation. So now you're here, you don't have plus 10, you have minus 10 volts here at the out. So what happens then? So when this happens, for sure the capacitor is going to discharge. He cannot discharge in the op-amp, he's got to discharge this way. So it's going to discharge. So that's what you see here. It's discharging. It's going down this way. And what happens to the to the other branch, the positive feedback. So what happens to this voltage here? Again, you have 4.5 volt coming from the voltage divider, but now you have current going from here, going this way. This is 4.5, and this is minus 10, so you have current going this way. So here you don't see 4.5, you see actually 0. And that's what you see here. I think it might be below 0 actually. So that's where we are here and here. So the capacitor is discharging, and the capacitor is discharging, and then as soon as it goes below that minus epsilon volt, the op-amp is going to switch again, and it's going to go into its high saturation. So now you're going to again get plus 10 volts there, and the process repeats itself. So it keeps doing this ad infinitum. Okay, so let's go back to the schematics. So this is your output, and it's a square wave. And here is showing that the possible output is some kind of triangular wave. And how does he accomplish this? Is with this thing here. You have that R56 and C19, and I'm sure you know what that is. It's simply a low-pass filter. And as you probably know, a low-pass filter is kind of an integrator, but not quite, because I mean, if you look at it, it's not really a triangular wave. It's more like it's exponential. It's a capacitor charging and discharging. I made a video about this not too long ago. The passive low-pass filter. I mean, if you want a true triangular wave, you would have to splurge a little bit and get another op-amp used as an integrator. So meaning that you need to have a capacitor in the negative feedback loop. So that's one type of wave it can generate, and the other type of wave it can generate is this thing here, which is actually a differentiator. It's a differentiated square wave if you look at it closely. Okay, so this is a bit bigger. So this is your square wave, and if you differentiate this thing, here you get 0, so that would be this part. Here you get 0, that would be that part. And for those edges which have a very high slope, basically, you get those spikes. So you get one spike here corresponding to that edge here, another spike going the other way for this edge, and then there would be another spike here. I don't know how this thing sounds, but I mean, there must be a reason why it's there. So how do you get this thing? Well, you differentiate the square wave, and this is obtained taking the output, that is the square wave, and passing it through a capacitor. So it's super simple. So square wave, capacitor, and you get this. Yeah, so I created another simulation that shows what happens to a voltage divider, like we had in the previous schematics, and you have another branch coming to it. So here I'm simulating the output from the op-amp with a voltage source, which is 10 volt. I mean, you can try also minus 10. So plus 10 is again the saturated voltage at the output when it's in the high state. So, and here what I did is that I used like a variable resistor here using a parameter. So here it's at 100K, which is the same as the circuit from before, but you can also step through various values to see what happens to the voltage here. So if you run this thing and you look at the voltage at the divider, you're going to get the 6.3 volts I was talking about. I mean, the 6.3 volts that we were seeing in the other trace. And if you put minus 10 instead of plus 10, you should get something like 0 volt, maybe a little bit less, like minus epsilon volts. So it's kind of interesting, and I put all kind of comments for you to read or not. But I think it's interesting It's an interesting little circuit to see the effect of this branch on the voltage divider. And again, the voltage divider formula is only when there is no current here. Okay, two things here. It would be better if the BP was not below the BN. It's kind of, usually you put the positive like voltage source at the top and the ground mode at the bottom. That's just a detail. And this thing, this low frequency oscillator, is actually a relaxation oscillator. So it's an oscillator on like on a cruise. Okay, so I think I'm going to stop here and I'll see you around. Bye.